So our last way we're going to look at calculating the reaction enthalpy is by using what's called bond enthalpy. So bond enthalpy is the energy required to break a bond. Okay, so the energy we need to put into a chemical bond to break it. So bond enthalpies, these are all endothermic. Okay, so to break a chemical bond between two atoms requires energy to do that. For example, let's look at a very simple molecule. Let's look at hydrogen. So for example, let's look at H2 gas. So it turns out hydrogen is held together by one single, what we call covalent bond. We'll discuss bonds and bonding and things like that in more detail in chapter 8. For now, I'm sure most of you recall that there's single bonds, there's double bonds, there's triple bonds. Okay, so hydrogen is held together again through that single bond. So the energy to break this bond right here is 436 kilojoules of energy. That is the bond enthalpy there. So 436 kilojoules per 1 mole of hydrogen gas that we have. That's how much energy we would have to put in to break that bond. Okay, so we put in this energy and then we have the hydrogen and the other hydrogen now split apart where each one of them took their bonding electron back essentially. So it takes 436 kilojoules of energy as an input to put in there. Okay, so what if we looked at the opposite? What if we took our H atoms and we combined them together to make now H2? Okay, well, we've kind of learned about energy. If one process is positive, the other process, or forming the bond, is negative. So the delta H here would be negative 436 kilojoules per mole. Okay, so breaking bonds is endothermic, forming bonds is exothermic. Okay, so what essentially we can do to calculate or look at the enthalpy of a reaction is we can look at what energy was required to break bonds, compare that to what energy was used or retrieved or received from forming bonds. The difference between those has to be the reaction enthalpy. So for example, let's take a look at Cl2 gas. So for example, Cl2 gas that we are forming 2 chlorine atoms in the gas phase. Okay, so if we look up in a chart for this in your book, so on page 192, if we were to look in this chart, a chlorine-chlorine single bond is 242 kilojoules per mole. So we broke bonds here. So our enthalpy, our delta H, is 242 kilojoules per mole. Okay, so once the reaction gets a little bit more complicated, we're going to need a nice formula to help us to do this. So we can look at the enthalpy of a reaction by looking at the sum of the energy required to break bonds, subtract the sum of all of the energy that we get from forming new bonds. Okay, so what this is going to sort of amount to is we're going to look at the sum of all of the broken bond energy here, so the delta H of bonds, broken. So bonds are broken on the reactant side. Minus the sum of our bond enthalpies. Bonds are formed, new bonds are formed on the product side. Okay, so we can get our delta H of a reaction by taking our bonds broken and subtracting our bonds formed. Okay, so let's look at an example. So we have the compound, a carbon with a chlorine and 3 hydrogens. This is in the gas phase. To that, excuse me here, running out of room. To that, we are going to add Cl2 gas, and then on, oh sorry, this is an H. I apologize. So we have methane and our Cl2 gas, and then as a result, we're going to essentially take one of those chlorines and swap it. So we have Cl, C, H, 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 and then the chlorine that, or the hydrogen that we took off the swap is just going to pair with that other chlorine. So then we'll have HCl. Okay, so we're going to look now, we're going to look at bonds broken and bonds formed. Okay, so let's look at broken. Okay, so let's look at bonds broken. Okay, so we are breaking this bond right here. Okay, so it's a CH bond here. It's a CCl bond over here. So this bond was broken. So in order to substitute here, we had to break this bond as well. Okay, so those two bonds were broken in this reaction. If we look at bonds now formed from this reaction, so this is a new bond that wasn't there before. So this one is new. And now this one here is new as well. So the enthalpy of this reaction should then be this bond energy plus this bond energy, subtract this bond energy plus this bond energy here. Okay, so let's start with purple. So delta H of the reaction is going to be equal to, okay, so we have one carbon-hydrogen bond that we broke. Pull up our chart. So if we look for carbon-hydrogen, that's 413 kilojoules per mole. Okay, so put that, 413. Chlorine-chlorine bond, we saw that in the example up here. That's 242. Okay, so all right, so that's what we had broken. So again, these are positive. These are all reported as positive value. We know that breaking bonds is endothermic, so we have positive values here. Forming bonds, by definition, is exothermic. So we're going to put that minus sign here. And now we're going to look up our bond energies we have over here. So we're looking for a carbon-chlorine bond. So if you put this up, carbon chlorine is 328. Okay, so we have a 328. And then our last one is a hydrogen and a chlorine bond. So HCl. So HCl is here, it's 431. Okay, so I'll put my parenthesis there. So again, these are positive because those are bonds broken and we know that's endothermic. This minus here makes these negative, which we know that forming bonds is an exothermic process. So that's why we have here. So we're going to do this plus this, subtract this plus this. We do that, we get negative 104 kilojoules for this reaction right here. So breaking these two bonds and forming these two bonds, exothermic process that releases 104 kilojoules worth of energy. Okay, so that's how this works. Let's do one more example. Okay, so one more example of this here. So let's look at a reaction that's a little more interesting. So let's look at the combustion of methane. Okay, so combustion, we're going to have methane, which is CH4. It's going to react with two oxygen molecules. Oxygen has a double bond. So we do that. We form carbon dioxide, also a double bond. So like this. And we also form two waters. Water is a single bond, so H, O, and H. Okay, so here's our reaction if we look at what we have in terms of single bonds, double bonds, triple bonds, things like that. So this one's a little more complicated. None of the bonds we have here seem to have survived over here. All these things started smashing into one another and recombining into a whole bunch of new sort of interesting things. So we're going to look at kind of summing things together. So I know pretty much all of these over here are broken. So let's just look at tallying it up. Okay, so if we look at carbon, if we look at a carbon-hydrogen bond, okay, so we have 1, 2, 3, 4. So times 4 of those are broken. Okay, if we look here, so that's all we have here. If we look here, we have an oxygen-oxygen double bond. Okay, so there's just one of them here, but that coefficient of 2 says I have to break this for each molecule. So this will be times 2. Okay, so I have to break 1, 2, 3, 4 bonds in this molecule. I have to break one bond here, but since I have 2 of them, I have to do that twice. Okay, so that's my broken. Let's look at what's formed. Okay, so I have a carbon-oxygen double bond. So that's the C double bond O. So I have 1, 2 of those. So times 2. We look here, I have an oxygen-hydrogen single bond, OH. Okay, so I have 1, 2 of those in this molecule times the fact that I have 2 of these. So 2 times 1, 2 tells me I am forming 4 OH bonds. Okay, so let's look at our chart. We need the CH, which we've already seen. So this is going to be, we have 4 times 4, 13. Okay, so again, we already saw that one in the chart. Oxygen, oxygen, double bond, we haven't seen yet. So that's here. That's 495. So we have 2 times 495. Okay, so 4 times 13 is 1652, and 2 times 495 gives me 990. Okay, let's go to the other side now. We have carbon oxygen, so we're going to have 2 times. So this is a big one here. So carbon oxygen double bond, 799. So that's a big one there. 799. So 2 times 799. And then we have 4 OHs. So 4 times, bring our chart back. So OH, 463. Okay, so 2 times 799 gives me 1598. And then 4 times 463 gives me 1852. Okay, so we're going to put it together now. E delta H of the reaction now. Our bonds formed, 1652 plus 990. We're going to, or excuse me, bonds broken here. Broken, subtract what's formed, 1598 and 1852. Okay, so if we, this plus this, subtract this plus this, we get that we have negative 808 kilojoules of energy released in this combustion reaction. Okay, so this is using just the energy contained in bonds to calculate the enthalpy. And this is actually a really good approximation because if you think about what's happening here, all we're doing is, again, breaking bonds and forming new ones. So if we can use the energy of our bonds, that's essentially, again, only really what's happening in this reaction. You do not get quite as close using this as you do if you were to directly measure it. So for example, for this particular reaction, the actual reaction is 889 kilojoules for the combustion of methane. So differences are that it doesn't really take into account states. So is this bond enthalpy for, say, a solid or a liquid or a gas? So it doesn't take into account kind of smaller things like that, but it actually gets you pretty close. So negative 808 compared to negative 889. Okay, so really, really close. Not exact, because again, if you look, it's not really considering if something's a solid, a liquid, or a gas, or that we do know that, again, when we look up in our enthalpy charts, we do know that there is a difference between the enthalpy of water as a solid, as a liquid, and as a gas. And this just isn't taking that into account, which was why we do get a little bit of error here. But it is a very, very good approximation because for the most part, breaking and forming bonds is what's happening in a reaction. So again, if you can look at what you're breaking and what you're forming and compare your energy difference here, then you can get, again, a good approximation of your reaction. So much more energy was released by forming these bonds here than it took to actually break this set of bonds over here, which is why we got that negative enthalpy of the reaction.